Next speaker is Markus Oberthaler from University of Heidelberg, and he will also be talking about entanglement and squeezing of large numbers of atoms, but in his particular system.
Okay, yeah, thank you very much. And before I start, I would like to thank Gretchen and Trey for organizing this thing and having this wonderful week here. Thank you very much for that. I also would like to thank the people who are responsible that I'm here. Thank you very much for giving me the chance to be here. And I will talk about in the next 20 minutes about the results we have achieved in Heidelberg. And I also would like to thank the people working in the lab hard that I can be here. And these are the PhD students, and David Hume was a postdoc for these experiments. And we had a very fruitful collaboration with Luca Betze and Augustus Merzi for one part of the talk I will tell you. And that's about extracting the Fisher information of an atomic system with more than 300 particles. And I also will tell you something about how can you do the squeezing we have done so far with 300 particles. How can you scale this up to large numbers? Because that's actually what you would like to have for doing really an improved measurement. And before doing that, I will give you an introduction. Okay, so I'm going to do lots of aerobics. I'm going to do aerobics with my hands, showing you what's going to happen. And what I do there is I show the motion of a collective spin. So we know for a two-state system, we can represent the state on a Bloch sphere uniquely. But I'm going to do many of these spinor halves and add them up to a big spin. And we call this collective spin. So this is built up by many spins, and thus you get an uncertainty of this spin. And if you take more and more particles, this uncertainty gets bigger. Okay, the good thing is that actually this uncertainty grows not as fast as the sphere size grows. And so at the end of the day, this is, if you want to do interferometry with these kind of states, interferometry is nothing else but rotating this state, and you ask yourself, how well can you distinguish different rotations? And that's all our goal. How can we do better measurements, interferometry measurements? And I will show you actually, by reversing that, showing that you can do better interferometry, I can say something about entanglement in my state, or if I have no entanglement in my state. Okay, so now, if we have this uncertainty, we know that this comes from these uncorrelated spins adding up. We can squeeze these kind of distributions by making correlations in these spins. And there are different ways of introducing these kind of correlations, and there are two general ways. One is using light interacting with the atoms, either measuring the atoms, do projective measurements, or you have back action, as we have heard before, or you use the interaction between the atoms themselves in order to correlate these spins. And I'm going to talk about this part, and then Philipp Treutern here is in the audience, did beautiful experiments on that, and Jörg Schmidtmeyer. Okay, so actually I will, at the end of the talk about how can we produce this squeeze state for large numbers, as large as 15,000, and then actually this is a scalable method which can go up to much larger numbers. And before that, I would like to ask the question, if you generate this kind of state, is this good or bad? I mean, if you at first sight, it looks bad because all the correlation, all these variances here are bigger than the classical state. But all of us would say, well, this has to be a highly correlated state, and thus there must be a way of using it. Okay, the spins cannot be independent, they have to be very specially correlated in order to get this shape. And I'm going to tell you how we do this state and how we analyze this state and extract the Fisher information, and show actually that we can generate almost a state like this, which is entangled. Okay, so how do we do this? We do this experimentally. We have a rubidium standard machine. We can produce blobs of condensates next to each other. And one of our expertise is that we can measure the atom number here, plus minus 4. This is done by normal standard absorption imaging, pushed a little bit to the limits. And that's actually what we analyze. Now, what we have shown recently is if we give up this kind of resolution and just capture these atoms, and this was done with a thermal cloud, but showing the concept. If we capture these atoms in a MOT again and measure the fluorescence, then we find actually the fluorescence has steps. And we can see the steps clearly for 100 atoms. So we can detect 100 and 101 atoms and distinguish that with a fidelity of 89.5% fidelity. And we can count up to 1,000. And this will be important in the future for going further and using all this entanglement we generate in our systems, because at the moment we are limited by this number up here, this 4. This actually kills lots of the resource we would have. And the resource is killed by the detection at the end. Okay, but for the time being, I'm not going to talk about this. I'm going to talk about that in each of these blobs, we take 2 internal states of rubidium. And we can detect these the populations of those 2 states by doing consecutive imaging of f equals 2 and f equals 1. And I'm going to talk about, essentially then, about one of the slices. This is the two-state system I had at the very beginning, and this will be spin up and this will be spin down, and the collective spin will be all these spins adding up to a big spin. Now, in order, and you will see that what we have to do is we have to do many experiments because we are analyzing noise, and the noise is our signal, so we need high repetition rate, and our choice was that we take not only 6 of them, but we take 40 of them, and produce these condensates in parallel. So essentially what we have is a repetition rate effectively of 1 BC per second, and it turned out to be very important that we have this kind of repetition and we have this common mode rejection, because all of these atoms see the same kind of noise of the environment. And so if you do correlated measurements, we can get rid of this noise, this common mode, we can do common mode rejection. And one thing I'm extremely excited about, and I will not talk about this, is if you melt this lattice, then you enter a one-dimensional situation with 2 components, and there is interesting physics going on. And we did some experiments in looking for critical exponents quenching close to a quantum critical point. Okay, so now going back to this two-state system in these 2 internal degrees of freedom. And for generating squeezing, we need this interaction between the atoms, and we need a description. And since I have introduced this collective spin, I can describe this interaction and this dynamics by using these collective spin variables. And so we have one term which describes the linear coupling, i.e. if I drive a 2-photon transition between those 2 states, I will go from here to there. And this is described by rotation around the x direction, and this angular momentum operator is a generator of a rotation around the x direction. And we have an interaction, so if particles sit on top of each other, they repel each other, get higher energy, then actually we get a term which goes with Jz squared. Jz is the particle number difference between up and down. And this actually generates the squeezing. And for rubidium, it turns out that, well, this high is actually 0. Because all the scattering lengths are almost the same, so they all kind of add up and subtract in a proper way, so it's almost 0. And there are different ways of solving this problem. Philip Treutlen, for example, uses 2 traps, species selective traps, and moves them apart. And, also, and what we are going to use is Feshbach resonance. So we have Feshbach resonance using those 2 states at 9.1 Gauss, and we can enhance this interaction, cross interaction between the components, and thus we can make this term non-vanishing. Okay, so now what kind of dynamics can you do? And the first thing is you just take the linear coupling, and essentially what you have is Rabi oscillations going up and down. And if you look at this sphere, I turn it around and look at the dark side of the sphere, I look on the other side, as you typically do. So I look at this side. And here there's not much difference, right? Just the sense of turning is a little bit different. But if you now add this nonlinearity, it matters. Because the nonlinearity has a certain sign, and thus this nonlinearity gives you a shear. As you go up, the shear gets stronger. Now, if you do this in a very special situation of going to the backside of the sphere, i.e. high phase difference, then you see that there might be a position where the nonlinearity compensates the linear coupling. Okay? It's also clear that you need enough nonlinearity that this can happen. If you have small enough in nonlinearity, this will not happen because it cannot compensate this linear coupling. But so there must be a critical value of the nonlinearity such that you get here a point which actually both things compensate. And classically, this is a fixed point. So if you go to the classical description of this problem, Jz squared translates into delta n squared, and this Jx translates into this term here with the cos phi, which is this Josephson Hamiltonian. And this one is now a classical Hamiltonian, and I can now draw the lines of this motion. And if this parameter, which is measuring actually the ratio between nonlinearity and linear coupling, is smaller than 1, then actually what you get is just slightly distorted Rabi oscillations, because the nonlinearity shifts more or less just a little bit on top of this linear coupling. But if you go above this critical value, then this stable fixed point splits up into 2 stable fixed points, and you get an unstable fixed point. And this unstable fixed point will be the way of you preparing this very special state with this S shape. Okay, so what we want to do now is we have this transition as a function of nonlinearity. Actually, this is the transition from the Rabi regime to the Josephson regime, if you want to talk about this quantum dimer dynamics. And we would like to put the state here and ask what happens. And what happens actually is the state is ripped apart. Okay, like classically, you will put different trajectories, and you would see you wrap around this fixed point or that fixed point. Okay, so now if you look at the sequence, what you get initially, you start with a coherent state. So we just rotate the vector in this direction, it's a coherent state. And then it develops squeezing, and then actually you get this twisted banana, and at the end you get this kind of question mark state, which is essentially a cat state. And this was already discussed by paper by Peter Zoller some time ago, 2003. So the challenge is now to see this experimentally. So now if you have these dynamics, how do you see this experimentally? Well, what we measure is always particle numbers. That's the only thing we can do, so we do it. So here's one result. So we have lots of particles up and few down. This is consistent with this picture, because it says you're in a superposition, you either see this or that. And since we have a copy of all of them, we do this the same, they have the same kind of common noise. We see now that it looks suggestively that we have this state generated because we are up, down, up, down, and so on. There seems to be no correlation. You do another shot, you get another up, down, and another one. And so it looks like exactly what you would expect from this state. But this state has more information than you can just see here, and I will come to that. So what you do is you do a histogram, and then you see, well, you have peaks here and peaks there. And actually, there's a nice way of understanding this, because you can show that in this now n-particle problem, we can map this on a single particle problem in an effective potential. So essentially, what the experiment was is actually putting a wave packet on top of a double-well potential. This double-well potential now is in Fock space, and so now you would expect that wave packet spreads out, so it squeezes, right? You get momentum position correlations, and then actually turns around and goes back. And with that, you get these kind of bumps here. Now, if you want to show that it's non-classical, because classically you would also get this kind of pattern, we have to show that you have n particles interference. And one approach was we thought, well, we can do tomography. We can try to do tomography, say. So we do, but before we do that, actually I should tell you, is this tricky or is this easy to do? And so nothing is perfect. And because if you look at this situation, well, you'd say it spreads out symmetrically. But it could well be that the double well is a little bit antisymmetric, so it's a little bit tilted. Then you would go to this side, or it's the other way, it goes to that side. And now you have to ask yourself, well, how much is this tilt of the potential in Fock space connected to your real numbers in your experiment? Well, the experiment was done in f equals 1, f equals 2 hyperfine states. So we are splitting here of 6.8 gigahertz. And so we have to ask, what does the tilt do? And the tilt is nothing else but a detuning between the two drives. And if you plug the numbers in for what you see here, it's 1 hertz detuning. Okay, so 1 hertz detuning is no problem for a microwave generator. But one problem is that we have the states which are second order Zeeman sensitive. And so 100 microgauss will do already the job that you do this 1 hertz, and then you actually get a mixture between this one and that one. But this is also no problem, because if you do active stabilization, we get over weeks a stability of 30 microgauss. There's also another way of compensating that. You do a Ramsey sequence, you do a kind of a bipulse in between in order to compensate this kind of magnetic field. So there's actually no problem. We can get rid of that. But there's another small detail, and this is, rubidium, I told at the very beginning, is all the scattering lengths are about the same. But they're not the same. They're about the same. So it turns out that the interspecies interactions here are not the same. And thus, the energy difference we get between the two depends on the total number of particles in your system. So now if you take in this well 40 atoms more, then we are 1 hertz off. That means I have to control the total number of particles in this double well situation better than 40 atoms, and then I can hope to see this kind of symmetric evolution. Okay, and there is no way that we can control at the moment that we have to have definite production of condensates with 40 atoms precision. But what we can do is post selection, because we can measure the atom number afterwards, and then sort our data as a function of sorting it by the atom number we had in our experiment. So if you do this, and you need some experiments in order to do all this tomography, so 90,000 experiments is quite a lot of big numbers. So we run this experiment 24 hours, 7 days a week for now more than a year. And so we can do these distribution functions, and this will be actually key for at the end extracting the Fisher information, and try to reconstruct out of these distribution functions the Wigner function. There are different ways of reconstructing that, but we suppose select this to 340 particles plus minus 10, and then actually we get this kind of Wigner function reconstruction. And the theory looks the same. And if you look at that, I didn't put a scale there, but this is all positive, which is it's not a so exciting result, because you would like to see negativity in the Wigner function to say, well, we got something interesting. But actually the theory already includes all the noise sources we have, and for this time, we don't expect any negativity anymore. There was already enough noise, enough loss even, to destroy these cats. But what we can show is that if you take 50 atoms less or 50 atoms more, you see exactly the behavior you would expect, and namely the mean field shift shifts the system such that you are not resonant anymore. Okay, so with that, actually, I would like to ask, if there is no entanglement here left, when do we lose it? Because at the beginning we have squeezing, and squeezing, definitely there is entanglement there. So do we have squeezing? Well, if you expand this bracket here, then what you see is, well, the variance just grows. But this is the particle number variance without any rotation. So actually the variance here grows in this direction, which is clear, but the squeezing is 90 degrees to this axis here. So actually you have to rotate that, but that's no problem. You just add another microwave pulse and you rotate this state. And what you see is you get squeezing, and you can compare it with theory and you understand it quite well. So now the main question is, what happens here? There's no squeezing anymore, but there might be entanglement. Okay, so now we do tomography, and we have to choose for our parameters a certain number, because only in this number we are symmetric. So now we choose all our experiment, we both select to 380 atoms. So if you do that, and we would like to show it entanglement, we might put it into an interferometer, and you would guess that if you do, you would like to measure an angle, you would rotate it first and measure this angle. Then you would say immediately, there is no squeezing, so there can be no gain. But this is actually a little bit too quick. Because what we should ask actually is, if you do these small angle changes, we have to ask how distinguishable are these distribution functions from each other. And just assuming a Gaussian is the first approximation, but if you have a non-Gaussian distribution, this might be not the right thing to do. So what you have to do is you have to ask, what is the distance between those distribution functions? And there's a measure, which is called Hellinger distance, which is a proper measure of distances for distribution functions. Okay, and that you can measure. So now how is this Hellinger distance connected to the Fisher information? Well, the Fisher information tells you something about, given you have a certain state and you have some operation on that and you have some measurement on that, how you extract from these measurements, how do you estimate from these measurements the phase you put in here? And actually, it gives you, the Fisher information gives you what is the uncertainty of this parameter you estimate properly. Okay? And this is given by 1 over m, which is the square root of m, which is the repetition, and f is the Fisher information. And the Fisher information measures somehow how sensitive is this distribution function to changes of your parameter you want to estimate. So there's a derivative of this parameter, and then you sum over all detections, over all mu, and this is the Fisher information. Now, how is this connected? Actually, for classical states, this Fisher information is maximally n. So if you plug this in, you get the standard quantum limit, which is 1 over square root of n. So what you would like to show is that this is actually bigger than n, the Fisher information. Okay, so how is this connected to the Hellinger distance? Well, it turns out if you measure the Hellinger distance as a function of the small angle change, then you would expect it depends quadratically on that. And the prefactor, the curvature of it, is the Fisher information. Okay? So now this tells you now what to do. What you have to do is you have to measure distribution functions, and you have to do this as a function of rotation angles. You have to be able to control. And if you do that, well, actually you can see the distribution function changes, and if you do this on the other angle, it also changes. But what you analyze is now the distance between the distribution functions. And this distance here has a dependence as a function of this rotation angle. And this curvature now is the Fisher information. Okay. So now, this is a relatively expensive measurement, but at least you can extract this value, Fisher information, without doing tomography. And with tomography, it's almost impossible because the error you do with your reconstruction is typically bigger, that you cannot give here a small error bar on this Fisher information. And it's a very general method. Okay, so with that, actually, you can show that at this point here, you still have entanglement. This is the Fisher information extracted from these measurements. And here is actually a rotation angle. You have to even find a proper rotation angle. And there is no squeezing left. Okay? And details you can find in this paper. We also showed that if you have this resource, you can do also interferometry. All you have to do is you go a little bit beyond the standard analysis. You have to do Bayesian analysis. And then you find out that the interferometer performance is actually exactly what you expect from this extracted Fisher information from this method. Okay, so with that, actually, I would like to quickly go how we do upscaling. And why is upscaling problematic? Why do we choose small numbers? Well, the first thing is that the noise there is relatively big and we can see the suppression easier. But the other thing is that the Feshbach resonances always introduce losses. And if you put more particles in the same trap, the density goes up and the losses go up, and so they kill your squeezing. So actually, the density limited. And then you would say, well, this is no problem, just take larger traps. But if you take larger traps, you enter the regime where you might see interesting other physics, namely many-mode physics and dynamics. So what's the way out? And the way out is following what the Roman Empire did. That the concept was divide and conquer. So what you do is you have this big system and you cannot control it, you divide it in small pieces, you can control, and with that you get control of the big system. Now slicing was exactly what I did at the very beginning. I had this condensate and had these 40 blobs. So we have these blobs, and we have the squeezing for this blob, but we have all the others. And what we can do is we can add up all these kind of individual squeezed parts and ask what do we get, and what we get actually is squeezing for all of them. So we can get squeezing of about 5 dB for 13,000 atoms. Okay? And this is scalable because this is just one-dimensional. It's our limitation that we have one-dimensional system at the moment, but you can extend this to 3D. So now with that you can do magnetometry, and there's a small trick to it, namely if you have this squeezing and you rotate your ellipse to the most sensitive position, then actually the nonlinearity will kill you because it starts to squeeze the whole thing and you have no time for doing accumulation of phase due to magnetic field. So what we did is we did squeezing swapping. So we swapped the squeezing to a state actually which is magnetic sensitive, which is one thing which is good. And additionally, it's not interacting because it's rubidium. There's no Feshbach resonance for lower states. And with that, actually, we can get good squeezing. We can get good visibility. We have a resource of 3 dB of squeezing for doing magnetometry. And actually, what we got out is we can do gradiometry with this device, with this setup, and we beat the classical limit for the particles we have, and we can add up. And this can be, the details can be found in this paper. So with that, I'm at the end. I told you about that we can analyze now, we can generate and analyze non-Gaussian state. The analysis is very general. We can do upscaling and get larger numbers. We at the moment we're limited by the resource we have at atom number, and we can count up to 1,200. And the latest activities are looking for scalings in these situations, and actually turns out there's a quantum phase critical point there, and we can extract the critical exponents. And with that, I thank you for your attention.
Thanks for the great talk. Time for a couple of quick questions.
Is your Fisher information limited by the state you generate or by your readout?
No, it's limited by our readout. Essentially, this was a big step to go from 5 to 4, because with 5 atoms noise, you would not see this Fisher information anymore. Because the Fisher information really tells you what you have at the very end. Essentially, what we do with the extraction is a real interferometer. And there you know you're limited by your detection. And that's actually also why we built this counter. Because with this counting, we can then build on this resource. And actually, it's also very interesting if you look at the squeezing, the squeezing goes away, but the Fisher information monotonically increases. So the resource increases, but then also your readout has to be better.
Quick question.
So I have to admit to being a little bit confused about the idea of entanglement without squeezing. I'm not bothered by entanglement without squeezing. What I'm bothered by is that it's still good for something.
Yeah.
So can you give us a little bit more of a sense of what's the nature of this entangled state? I mean, is it just that the squeezing is hiding someplace in another variable, or?
No, but they take a cat state. A cat state is the worst thing in fluctuation. It's maximum fluctuation. Still, it's the best thing you can do for interferometry. And why is that? Because the pattern you get is not a Gaussian, it's a cone. And actually, if you go 1 over n, you shift the cone by 1 unit. And that is perfectly distinguishable. And that's actually in the direction. This is a transient state where you start from the squeezing, you go over to this cat state.
Okay.
And so essentially what you get is you get structure in your distribution function. And the structure is more than just Gaussian.
Okay.
Now in this very special case, we are just at the beginning of it. So it is more or less there's a peak and there's a pedestal, and the pedestal kills your kind of normal
Okay,
variant
so this is
analysis.
something that's more or less cat-like and is getting the interferometric gain from
Yes.
its cattiness.
But it's not yet cat.
But,
But
it's
this is the essence of it.
It's a little catty.
Yeah.
Is
I would not call it a cat. I mean, if you look at how many particles are entangled, you can do the same thing as with the depth of entanglement with this Fisher information. You find out it's 2. Yeah, because it's and why is that? This is because we are at the moment limited by this detection noise. Actually, there might be much more in there, but we don't see it because you have this structure, and you also know if a cat state and you have this odd-even effect, and you have a detector with sigma of 4, you don't get anything. So you need this detection of single excitations in order to be able to use it.
Yeah.
Okay, thanks for this very stimulating talk. In the interest of time, we have to move on. There's probably questions for later. Thanks again.